we kind of have this idea in undergrad principles that a tax can reduce any economic activity that produces a negative externality. And with perfect information and a lack of frictions in the market, you could impose a tax or a quota to restrict the quantity of some output, right? We talked about Coase's paper, the problem with social costs, a little bit of history about it. What Coase really said is that it takes a lot of deep understanding of each particular issue in order to really digest who's being harmed and how much they should be compensated for this type of interaction. But in a sense, a lot of what Coase came out with, or what we learned today, what's called the Coase theorem, was really popularized by George Stiegler at the University of Chicago. And there's papers by Donald McCloskey, Deidre McCloskey, other people that say, look, the way Stiegler presented the Coase theorem is a little bit misunderstood. And the way we teach it, the way I teach it at least, we say, look, in the absence of costs for bargaining and transactions, and if property rights are well defined, if you know who's being harmed and who's causing the harm, then the private market outcomes can be efficient. But what Coase says is that you're rarely going to find a situation in which you have this really strict assumptions. So we're in a world of asymmetric bargaining. Firms have a lot more information and power and better lawyers than individuals. And so we really need to think about these cases on a case-by-case basis. Wow, house just opened up. Okay, so we have a two-sided problem. Some places, or some people will call this a bilateral monopoly problem. And in a sense, when you get down to it, workers or the community does have some power, and it imposes a constraint on firms who are producing this economic good. If you have the ability through the legal system and institutions to impose fines and penalties, the question becomes which side of this problem is actually going to dictate how the outcome arises. Coase says, look, it doesn't really matter who has the final say or who has the property rights. When you have costless bargaining, then you end up with an efficient outcome anyway, regardless of who's assigned the rights to kind of carry out the transactions. Okay, now is the challenge or the interesting thing for future research, and there's more and more papers coming out about this $1 million plant. It's basically the idea that some places, they're going to offer a bunch of different incentives to attract large firms. And essentially these firms are scoring locations based on all of the different qualities. And so if you can reconstruct, however you do it, the scoring system, then you know which places basically just missed out on getting a large plant operation. So you can compare right around that threshold and look at what's the payoffs in terms of spillovers and productivity, labor markets from getting $1 million plant. The key thing in a lot of this discussion is that the ability to punish firms for producing negative externalities does play a big role in firm locations, right? Different states take different approaches to environmental externalities and things of that nature. And you better believe certain areas are going to offer like weaker regulations in order to attract firms. It's just a fact. Okay. The targeting principle, when you think about regulation, you just want to target the place of harm if you know it, or if you can. The challenge is that special interest groups kind of give you a lot of pushback in terms of how do you target policy to get the outcome that you desire. The example we used was taxes on gasoline. We basically came up with a few different reasons why you might think this exists. One, the regulation of harmful pollutants that come through driving miles. Another may just be the sheer amount of miles driven, things of that nature. There's also people who believe taxes on gasoline were instilled for some like conservation type benefit. And people in this literature, the real public choice folks, have a bunch of arguments against why when you mistarget regulations, it can cause more harm than good. The last thing in terms of like our theory we arrived at, when you think of improvements in efficiency, the big question we said is not gonna be a Pareto type efficiency. Polluting the environment to produce an economic good is going to harm some people, it's gonna make some people worse off. Especially in the case that we're going to discuss in this paper, is like nowadays a lot of the refined oil products are being exported, and even though it does provide jobs, that's a compensation for dealing with pollution in a sense. So if firms can compensate local residents and still make a profit, total social welfare may increase. You know, now you're getting into the world of Caldor Hicks. Okay. So this is the big figure we start with here. We kind of covered. Basically on the left-hand side of this, you have the total number of refining sites. And you can see from those bar frequency graphs that from 1990 to 2010, the total number of sites decreased by about a third. And then this line graph, which is represented on the right-hand side of the y-axis, you can see that the total capacity for refined products in the US has increased during this time. So this is just a way to show what we mean by industry consolidation. Question, how does this impact local welfare? And we talked about this. I want to get through this so we can talk about the results, and then also want to talk about discontinuities. Here's the data, if anyone is interested in this type of stuff. Energy, I have more data too. Just before I came back to academia, I worked in the oil and gas sector, and I actually worked in that sector for 5 years before grad school, so it's like, I'm really interested in a lot of this stuff. Here are where the refineries are located, and just wanted to show on the right-hand side of this, you can have large refineries in big cities and small towns. So this is important for labor markets, right? So if you have a 400,000 barrel per day refinery located in a small town, if this thing closes down, the labor market is probably not going to be able to absorb that loss the same way a similar refinery in a major city can, right? This is the question of frictions. If your labor market is set up solely around refining activity and that thing closes, there's going to be a lot of adjustments that are going to be painful. But if you have a place where there's a variety of industry, then people may be able to find a new job, right? Depending on the share of total employment that comes from the refineries, right? So there's a lot of considerations. And we're very early in this project. Just a quick discussion of how refineries work. Oil comes in, gets heated up under extremely high pressure, and the temperature at which you distill the crude oil determines which product you get out of it, right? You get gasoline at some of the highest temperatures, jet fuel, kerosene, and other things. You know, this whole process was designed in order to produce a cheap gas to run plants that were refining other stuff, right? This was thought of as a byproduct at first, but then as the demand for whale oil continued to rise with US income, but the supply of whales was falling because it's a livestock and people are going to overfish it, just slaughter it to sell it. And we needed a substitute, and that's how we ended up with gasoline. And it just so happens that we figured out how to refine this stuff around the same time we got the gas-powered engine, okay? And so here's just a glimpse of what the refinery space looks like, just to show you that all of these connectors and pipelines actually have potential to leak. Here is the ring design. I'm going through this fast because we went through this last class. Essentially what I'm going to do is show the summary stats for the setup and basic regression, okay? So the inner ring are those closest to the refinery, and as you go out, you're going to be in the outer ring. So a simple regression is just taking different neighborhood outcomes and regressing it on a set of categorical variables for whichever ring you are. The reference group is this outer ring from like 3 to 5 miles. So here are those betas, and we showed that in ring one, closest to these refineries, you have higher levels of sulfur dioxide, ozone, nitrous dioxide. When it comes to carbon monoxide in column 4, it was more so about, my guess is that when you get closer to the refinery space, you have manufacturing activity, and carbon monoxide may be related to passenger vehicles. Nevertheless, you could see the pretty clear relationship between refinery activity, proximity to it, and your environmental air pollution. In terms of this diagram, or this table, I just wanted to show, all right, by definition, we would expect a house price gradient where house prices would be lowest, closest to the source of pollution, and they should rise in distance to the refinery or distance from the refinery as you move out, you're more further away. What this helps us do is start to define what is the area of harm, right? So when you get to the outer ring, ring 4 relative to ring 5, then you don't really see much difference in the house prices on average in those two rings. So essentially for the difference in difference analysis, we're going to treat this inner ring as the treated areas and these outer rings as our comparison group, right? And this is kind of a little bit of justification for that. And you see the same pattern for income, less of a clear pattern for the share of white households in the community, but in general, these three are pretty strong. I'll probably take column 4 out. So essentially, and I was talking with someone else about this yesterday, what we're doing is the ring design and differences, but I'm gonna show you some other results too that are basically taking different parts of a labor market or a housing market and considering them treated based on jurisdictional boundaries. And this is an interesting feature of this, is that so let's take this big square and let's call this a labor market or a housing market. So this would be the Tampa, St. Pete, Pasco County, like just a general larger market, okay? And we'll measure this through a number of different ways. This could be the MSA, Metropolitan Statistical Area, the Census Business Statistical Area. It could be the Bureau of Economic Analysis, labor market definition, just a number of different ways you can define a labor market. Commuting zones. So like this is up to the researcher, and you start to see that you have different margins of definition because these are all different. So essentially, you have this refinery space that we've talked about so far. This is the plant, it's polluting the ozone, and then there's a certain radius in which that is having an environmental effect, okay? And I'm claiming that this is like 3 miles. The way that the ring design is set up is so that this other area, this is like another 2 miles in between the refinery and this first zone, so this is 2 miles. This is our comparison group, okay? So when this thing closes or expands, how does an outcome change relative to these outer rings, okay? And we're gonna measure the inner ring details by all of these like blocks. So we have census block data in here, census block data out here. And so it's just the average difference, right? It's just the average change inner rings versus the average change in the outer rings relative to a closure or expansion. The second part of this is that this is just about space, right? And mileage and distance, but then we have another within these labor markets. Maybe you have one school district, and so maybe you have school district 1, school district 2, school district 3. Within these labor markets, this refinery is potentially contributing to local tax revenues here, but not here and here, right? So now we can say, how does the property tax revenues or total revenues change here relative to these other areas, right? And so this is just basically taking a difference in difference design and allowing the treatment and control to vary based on the data. I mean, it's like, if we had perfect data, we know a bunch of stuff more granularly, but since we're looking like this, it's not perfect. Now, what's the economics? Essentially, let's think about where people live, okay? And so there are people living within this ring, and they're getting the pollution, and they're getting possibly the public good revenues, right? There's people living out here who are getting the labor market access. You could drive from here to here, drive from here to here, but you don't have to deal with the pollution, and you don't get the property tax revenues. And there's also people here, right, that get the property tax revenues, the labor market access, but not the pollution. So once we really kind of pin all of this down, it's like the whole idea is that the welfare impacts of this activity is not like just smooth across space. It's really going to be discontinuous in a lot of different areas. And it's interesting. You could, get all of the benefits without any of the costs. And by this is that there's going to be strong income sorting. So if we say people who are getting these benefits of being near the refinery and getting the property tax revenues without the environmental harm, then we're talking about inequality because they're going to be of higher income based on the income gradient, right? So this is like a way to think about the environmental inequality literature, the public goods literature in terms of plants and like Coase theorem, labor markets. So hopefully we can nail this paper and really put it in a decent journal. Okay, so in order to carry out the study, we need the activity, right? We need the closures and expansions. So here are the locations of these refineries. The red dots are those that closed, and the black ones are those that remained open throughout the entire sample period. These regions are called PADD regions, P-A-D-D, basically broad areas classified by the Energy Information Administration to say like the activity over here is very similar across states. Same thing about here, these are just regions. So production has decreased quite a bit on the eastern and western seaboard, started to consolidate towards this Gulf area. And then we're going to look at how these closures affect the local environments. And of course, the ones that stay open, some of them are going to expand because we saw total capacity increase. So in terms of the pollution effects, here, this is a difference comparing the inner ring to the outer ring. Okay, it's a very local assignment, right? And you can see that when a refinery closes, about 5 years out, you see a 2% reduction in sulfur dioxide. The biggest effects come from nitrogen dioxide, which is a decrease of about 3.5%. Okay, so as you might expect, some of these are self-evident. After the operations expand, you see an increase in sulfur dioxide of about 4.3%. This is outward, so 5 years after the expansion. Ozone increases by about 1.7%. No real increase in nitrogen dioxide. Carbon monoxide, I don't know how to explain that result just yet. Okay, so you start to see some trends you might expect just from using the differences. When you talk about income, okay, so now just pay attention to column 1 for now. Column 2 and 3, a little bit harder for me to explain. But so for income right now, we're just within markets looking at this inner 3-mile ring relative to everybody else, not just this 2-mile ring, okay? So the inner 3-mile ring relative to the entire labor market. This is because of a data constraint. For the pollution, I have a lot of high frequency data, but for the income, I don't, okay? So in the inner ring, after the plant closes, you see about a 2.2% decrease in the income measured by the average income of home buyers in census tracts within the inner ring. After an expansion, we don't really see some similar increase in income in the inner ring. So yes, there are gonna be more jobs potentially likely to be close to the refinery, but as we know, high-income households don't wanna live near the pollution effects. And we see after the expansion, pollution is going up, so there's not a real big income increase, after the expansion. House prices, okay, again, looking at column one, you get a closure, as you might expect. This is gonna decrease the demand for those neighborhoods near refineries. A lot of people were just living in that inner ring to access the jobs, dealing with the pollution. So if that plant closes, you get a decrease in house prices about 6%. That's not small. After the expansion, now we talk about the fact that people are trading over proximity to jobs, knowing that you're going to get higher levels of pollution potentially with this expansion. And we see that the proximity to increasing job bases is much stronger than the negative amenity of being close to pollution. So after an expansion, you get about an 8% increase in house prices in those inner rings. Okay, now these tables are very messy, so just bear with me as I try to explain them, okay? So right now, I want you to just think about a cross-section, and I think this is the year 2010, okay? And so this is not difference in differences, this is just a cross-section of data for a given year, so it's a snapshot. And each column is going to be a different school district finance variable. Total revenue, property tax revenue, state revenue, federal revenue, okay? So these are the way schools raise money through these three buckets. In general, on average, in the United States, the majority of funding for schools comes from states. That'll be about 40 to 45% of the total revenues. Property tax and local taxes are very close behind. They're about 35 to 40%. And this all depends on the state. Federal revenue is closer to like 8 to 10%. All right, so this is not a huge portion of school district funding. States and local taxes tend to contribute the most. So if we take these as different regressions, and these are different outcomes, and they're logged, okay, very sloppy here. You have a dummy variable for whether or not that district contains a refinery. So that S3 gets a dummy equal to 1, the others get a 0. And then comparison, also going to add an interaction with whether or not that refinery is above the median size, okay? So these are the large refineries. So in the cross-section, this is just summary statistics. The average refinery district compared to all the other ones and refinery states only, they're not very different in terms of how they raise money. But when you look at those large districts, they get a lot more property tax revenue, 16% higher, total revenues, 16% higher. Property tax revenues, is this right? 16%? How many spaces do you carry this over? Yeah, 45% higher, and then no real different in state and federal revenues, okay? So you have a large refinery in your district compared to other places with refineries and all other places without, you have a pretty substantial increase in some of these local revenues. This is not to say anything strong, this is just a summary statistic. So we look at these same markets after closures and expansions for obvious reasons. But then we don't really get any precise results here. So at 5 years post-closure, you don't really see much changes in expenditures, which is probably a good thing. You don't want the closure of a local plant to like really just disrupt your public goods. And I'm only looking at large plants here. You see a small decrease in property tax revenues. It's not significant, but it looks like it's offset by state revenues in some sense. And I just wanted to kind of look at other margins. This is how much you're spending on capital investment, buildings and land, and how much you're spending on salaries for teachers and administrators. This is 15 years post-closure, still nothing significant. So there are changes happening. They're there, decreases in property tax revenue, potentially offset by increases in state revenues, but it's not anything that's like really, really a strong result. Similar with expansions, right? It doesn't seem to be that it increases your total expenditures, but property revenues increased by about 7%. And in the long run, again, it's pretty inconsistent. Okay, so this is a work in progress, as you can imagine. I mean, I've just presented you some pretty fresh results, but I find it interesting. Obviously, it's something I'm working on, and I think I want to get 1 or 2 papers out of this. So, any questions about this idea and how? Any questions about this idea and the ring design method and this difference in differences with treatment and control being assigned based on space? The idea of the estimator is one thing, but the concept, making sure you understand what I'm doing or what we're doing and what we're trying to pin down here is important.
So you said for the inner and outer ring, we're gonna compare the two, the difference to see. We're gonna just see like living in an inner ring compared to the outer ring, and then you said with a dummy variable, S3 gets the refinery revenue, and then S1 and S2 don't. So they get 0 because out of a binary variable. So S3 is a sweet spot to live in because you'll be able to be away from the pollution but still get the.
This is a question. I mean, I think if I had to guess, this is what you consider to be a sweet spot because you're in close proximity to the jobs, but you're also away from the major effects of pollution. So if you say it's the welfare effects. If we just looked at house prices, we see house prices being affected really around this ring. And then, so the capitalization of the positive property tax revenues is pretty evident here. But we still need to pin that down. That's the objective, to look at the welfare differences in these different spatial areas. So just to give you, so let's say, so how we think about this? So the expectation for some outcome Y, conditional on being in the inner and conditional on being after the expansion or closure, minus, so this is going to be one difference, the expectation for Y conditional on being on the inner but being in the pre-treatment. So that's the first difference, right? What is the average house price income in the inner ring after the expansion or closure? Minus the average house price in the inner ring before the expansion and closure. That's the first difference. The second difference is the expectation for the outcome minus the expectation in Y. So this is the basic idea of a difference in difference estimator. This difference captures changes in the treatment group. This difference captures changes in the comparison group pre and post. When you subtract them out, you're differencing out effects to the entire space, right? So if something, for instance, if, let's say throughout the time pre and post period, you have a recession. That recession affects both areas, the inner and the outer ring. And so by differencing the inner changes from the outer changes, you're controlling for the effect of anything macro, right? Now the question is like assignment to the inner ring completely random? Not necessarily, no, okay? So the people who are living in the inner ring may be systematically different than the people who are living in the outer ring, right? But the argument is that the timing of the expansion or closure is unrelated to those differences. So if that's the case, then we can still argue that this is pretty good. So that's the inner and outer ring. Essentially, all the other analysis is doing the same thing. except changing how we categorize inner and outer. So we stick with the 3 mile radius for the inner. In some cases, the outer is all of S3 except for the inner, if that makes sense. This is still a work in process, so you can see I'm being very ad hoc how I explain it, because I'm figuring that out on the fly. Yeah, but this is like the basics of a difference in difference estimator. It just got more and more complicated as we really unpack the staggered difference in difference, right? So if you were just looking at a case study where you have one refinery, you got plenty of data, and so you can compare the inner and outer rings pre and post, that's your difference in difference estimator is just this. Like, and that's perfectly okay. I mean, you just compute that average, those differences in means, and you're actually pretty golden. The challenge becomes when you have multiple refineries or multiple treatment areas, and then the treatment happens at different periods in time, and all of these other assumptions get violated. So then you have a staggered difference in difference, where you're making these comparisons across different regions at different points in time. What's the challenge with something like that?
Could you repeat that one more time? You said that we're gonna see the change in effects over time.
So let's build this up. This is I think this is a good and important way to think about this. So if you have one case study, let's say the largest refinery in Port Arthur, Texas, and you have plenty of data for the inner ring and the outer ring, and that refinery closed down, okay, and it was unexpected to everyone. You could compute the effects of that closure and have a causal estimate just by taking these differences in means, right? Okay. Now, if you have a bigger study and you want to move beyond just one plant, so you have 100 refineries, half of them closed down during a sample, but they closed down at different points in time. And so you're going to basically do this procedure for all of those different plants and like come up with an average effect, an average treatment effect. What's the challenge with that?
I guess just different conditions and like throughout different periods of time, like depending on like, you know, like, I don't know, like even something like interest rates, certain facilities could be more resilient to like change or closure, or like communities may have a different reaction to, you know, something like a closure.
It turns out, what you want to add to
No,
it?
you can go.
Go ahead.
It wasn't anything.
Okay, it turns out like you're right. Are some things that may be unique about the time in which the refineries closed down. And that might be systematic for every place that closed down. And so you might not observe that in the data. So if it turns out that all the refineries closed down in different points in time because the local interest rates are screwed up, you don't observe that in the data, but you're gonna attribute all the changes to the shutdown when it could be because of the interest rates. And it's like we like more data, the better type discussion, but as you stack on these like closures and expansions, it becomes a lot more likely that there is some correlation between an unobserved effect and the treatment. Okay? I think that's a kind of a good way to think about a question I could ask. It's like, if you have a difference in different design, I would never ask you to like, you know, describe the Callaway and Santana estimator, but I would say something like, consider a case study where you have this type of setting. What is the estimator? If you just have a bunch of good data and one treatment, it's just the differences in means. And then I could say, okay, now you have a bunch of different closures all occurring in different places around the country at different points in times. How does that generalize to something like this? And what would be your concern if you just did the most simple thing? All right. Okay, good stuff. How much time we got?
Professor,
Mm-hmm.
in the paper that you gave us for the homework, like the paper on the Beijing's.
Yeah.
So that paper, I think that paper had similar kind of problem with the different timing with each of the lines of the metros. But I think they solve the problem using a trend for like each of the area. So I was wondering that if you could use similar kind of approach to solve this problem.
Like basically the inner ring and outer ring at a given refinery follow a
Yeah,
same
so
trend?
I think as far as I understand, I might be wrong, but they kind of add a time trend for each area. So which
Yeah.
kind of captures the like any kind of like shocks that comes through that 10-year or 15-year period.
No, I think actually, I think that's not a bad idea, because it helps address the fact that each individual area, particularly for our case, may have a different, kind of effect of the recession.
Okay.
Right, this is a big question we have, is like, we're looking at all these things around this long time period. There's clearly a huge recession in 2008, there's another one in the early 2000s. And so if all of this is happening, you're saying you can make an assumption that those kind of macro trends affect each market the same, and then we can identify each local market the same, and then we can identify all the differences in the treatment type thing.
So as far as I remember, what they do is that they kind of use a like a coefficient that kind of captures the effect of the time period, like the 10-year time period or 15-year time period for each area.
Oh, I see.
So that's how they capture the time varying effects.
Yeah, no, I can check that out. Let me, I think that's actually might be helpful. I like that paper. It's a decent paper, and I think
Yeah.
it's set up for something that you can understand and try to apply. Okay. Yeah, I actually used that for one of the midterm papers, when I taught this a couple of years ago. And so I talked to Professor Wigger, who will give you a lecture on Tuesday, and she's supposed to send me some materials. You're lucky because she does a lot of work very similar to me, and she's gonna give you a little bit more causal inference type way to think about it. I'm gonna show you just so you can have some prep, and I think I'd like to squeeze this in right now anyway. This idea of boundaries as discontinuities with the application to the bigger literature of regression discontinuity designs. This is kind of a good way to think about it, as we're talking about pollution, spatial things, and it's all right in that same ballpark. Okay, so I'm gonna move away from this and go to a different setting. I drew this figure on the board last time, so I'm gonna draw several of them that all kind of follow a similar pattern and talk about an easy way. So, as you notice, I'm kind of visualizing these setups, these designs, and then showing you like the most basic way that the thing of interest can be estimated. I'll do the same thing here. As you pointed out, it gets more complicated, right? But as you continue to go and you take hold of your own research and stuff like that, the expectations are much higher. But I just want you to understand the intuition. Okay, so we're gonna think about regression, discontinuity via boundaries. So I'm working on a paper with a friend of mine, very specific to this idea. It's not a new one. Well, the paper I'm working on is new, but it's not a new idea. A lot of this research came from the education literature, looking at how house prices change on opposite sides of a school zone boundary, when plausibly the only difference is differences in test scores. Okay, so I'll draw these figures smaller now because I want to draw several of them. So let's think of this source not as a plant now, but a boundary. So it could be a school zone boundary, but I'm gonna start with railroad tracks, because they carry a certain feature that makes this easy to test. So you have some railroad tracks at distance equals 0, all right? And then on this axis, I'm going to use two things: the disamenity which I'm just gonna call delta right now, and then the price. This is very, very ad hoc, so, but I think it is gonna articulate the point. So at this railroad track, you're going to get a lot of kind of environmental disamenities, not necessarily like smoke and smog, you're gonna get that too. But the fact that the railroad track kind of malfunctions, it breaks down, there's a lot of noise. So the disamenity delta for living close to the railroad tracks is the highest here, okay? So this is the curve for the disamenity, just gonna call this delta. In a sense, the price of housing in this area should follow the opposite pattern. And we talked about this, so I'm not gonna spend too much time belaboring this point. As you move further away from the railroad tracks, the house price gradient is not gonna ever be down at zero. But the house price gradient should start somewhere and then increase like this, right? And this is not linear, obviously, so this would be the price of housing and the function of not distance. The price of housing as a function of delta and also other neighborhood characteristics X, okay? So this is the disamenity and this is other amenities. And you could just make the assumption that dP dx is greater than zero. So more, or as X goes up, you got higher quality amenities, prices go up. Okay, and so this is pretty straightforward, right? Any questions about this? Pollution wanes with distance from the source, prices increase from distance to the source. So, you know, in the United States, I don't know about other countries, but railroad tracks actually are like neighborhood boundaries. They're like a landmark. People say you live on that side of the tracks, or you live on the rough side of the tracks, you live on the good side of the tracks. But it could be a railroad track, it could be a highway, it could be a number of different things, right? And they're going to serve as physical neighborhood boundaries. Now, here's the thing. If the disamenity were the only thing that generated the price gradient, we would have something like this, because there's two sides to the track, okay? Where's the trash can? All right, there's two sides to the railroad track. So you can live on this side, and I'll just call this side negative distance. Okay, just moving in the opposite direction and the other way, same amount of space. And so here's zero. So essentially, okay, the disamenity should be what I'm calling symmetric, right? So like the disamenity should follow the same pattern in theory, and you may argue that it doesn't, but I'll say this is delta, and then, so this thing should actually follow a symmetric pattern, right? Because the railroad track affects both sides of the boundary the same. If you know, you could be the economist that says it doesn't, and you might have reasons. But let's just assume that it does for right now. And so if you had the condition where, let's say the symmetry condition, if X okay. If these other amenities were randomly assigned, meaning that they did not vary with distance from the boundary, then the price gradient should be symmetric because it's only capitalizing changes in the amenity, right? So if that's the case, then we should have something like P, this is going to the right. Does that make sense? I'm saying it may not, I'm not an artist. But so if these things are not being influenced by the boundary, then the price gradient should only capitalize the disamenity, and then we should have like a symmetric type of thing here. So what are the X's? So let's talk about that. So X's are neighborhood characteristics outside of this pollution, disamenity. And so let's say that the X variables are things like income, which from that, you know, it varies in distance to the source. It could be racial, demographics.
That's an amenity.
For sure. I mean, yeah, we're calling it an amenity, but people
Yeah,
people care about the racial composition of their neighbors for sure. I mean, yeah, it's actually another two-sided problem. We're getting new research now that says, hey, there's a word called homophily. Have y'all ever heard this word before?
Mhm.
What does it mean?
You have a preference for like the same thing or, you know, a given composition and stuff.
So
when you spell it out, I understood.
yeah. It means that people love to be around people of a similar characteristic. So homophily research is now showing that it's not like, oh, you know, white people hate living around black people, or, you know, black people hate living around Latino people. It's more so about that people of all backgrounds and incomes tend to like to live near similar households. And so there's like a two-way thing, and anyway. But so racial demographics are an amenity. It could be housing stock. You know, there is no reason for houses to be, because prices vary with distance, then we necessarily know that housing stock might vary in terms of quality, but the changes should be symmetric, right? You should think about it, that if these things are randomly distributed, the changes in these should follow something similar to what the price gradient does. And then, you know, housing stock and also public goods. So it could be the case that the railroad tracks overlap some school zone because the administrators are lazy. And so they say, well, railroad tracks break up the city anyway, let's just make the school zones the same. And so railroad tracks may dictate public goods. All of these things could be randomly assigned over this space, or they could vary across the boundary, right?
Out of curiosity, is delta like a summation of all the pollution that might come with
Yeah, for now.
railroads?
Yeah, let's just say all of the negative stuff. And let's say it's invariant to side, which is arguable. Okay, so now it turns out, and this is what, you know, I'm kind of making a claim for in some of my current work. And we think about residential segregation as something that's like status quo in the United States. It could be income segregation, it could be racial segregation. In this setting, it means that the X's are not randomly assigned. Something else besides these things we observe is dictating how neighborhood income is arranged, racial demographics, housing stock, and public goods across this space. So what we end up with, I need one more color. Okay, whatever. So that's the price. So in this world, what we end up with, yeah, let me just erase this one. How much time we got? Okay. So let's erase this one. This is just the background. So what we end up with, okay, so let's do it like this. Okay, this is 0. And I promise you this will all make sense in a second in terms of this class. So what we end up with is the X's are not randomly assigned. So let's say now we're gonna look at log of income. And I can measure the income of people at a fine level across space, maybe it's at the block group level, so I got plenty of measures of the income variation here. What it ends up looking like is something like this. So I'm gonna say the income across space is a function of the X's, obviously the price and the amenity. And so that's on one side, and then on the other side, it looks something like this. So this is not symmetric, okay? The slopes look very similar in the data, but there is not, it doesn't reflect cleanly across the axes. It turns out there's a discontinuity here, okay? So I'm arguing, and what I'll show through a bunch of other measures, is that this represents something else that's outside of what's caused by just the railroad track or the highway being there, right? And so if that's the case, then this jump, well, let me not get ahead too fast. Okay, so if that happens for income, I'm just going to overlay this on the same. Naturally, since income is an amenity, the price gradient does something similar, okay? So the price gradient, let's just say, it could be above or below, but it looks something like this. And then let's say this one is below this one. So the price gradient is not symmetric, so it's capitalizing something other than just the pure disamenity. And here now we have this discontinuity. We'll call this jump, and the outcome variable at the cutoff. Okay, perfect. So obviously, there's a gap here in terms of what's happening, and we're gonna try to understand what that is, and we're going to understand how big this jump is, and it matters, right? Because it has a bunch of economic implications. If the prices are jumping by this high just to get on this side of the tracks, and we say, well, railroad tracks, they're going to be assignment of public goods because the railroad tracks overlap school boundaries, then this discontinuity becomes like a premium just to access these public goods. And now we're talking about inequality. So this could be railroad tracks, this could be school zones. It could be county lines. It's weaker, of course, at county lines. A bunch of different things, whatever you think of. And then you could set this up and look at these discontinuities and then estimate the price premium for living on the good side of the tracks, or estimate the price premium for living on the high quality side of the school zone. And this is important because it means that there's a level of inequality here that is being created by, just behavioral responses to the environment. Okay?
Could like tax zones be a part of that?
Say it again.
Like taxing districts that be a part of that? Because
Oh, definitely.
I see that a lot down, like when you're in and out of incorporated areas, because there's less, obviously there's less taxes, but there's also like less permitting that you need and the random crap.
These are, so in my mind, there's a whole research line that deals with these type of things. And people use these discontinuities to look at the differences in taxes, study tax competition. So like, you can think of one side of the boundary having a lower retail tax, another side having a lower property tax, and how does that spill over in terms of consumption and tax revenues? These are questions because, as we talked about, jurisdictions compete for residents. You compete for the tax base, and so if one side has a higher property tax rate, what happens over time, you might expect the other side to either raise it or the other side to lower it, like it is competition there, okay? So this is a form of regression discontinuity, okay? The running variable in that terminology is just distance to the boundary, okay? So essentially with the regression discontinuity, if you weren't using a boundary and distance, you could have some other way to categorize people, we just call it a score. And then at some threshold of the score, you get assigned the treatment. And then on the other side of the threshold, you make a nice control. And then so the goal is to determine how far on each side of the threshold we're going to go in order to determine like, okay, we know this is the treatment group. We can see that in the data. How far do we go on each side in such that the treatment group is the same as the comparison group and in econometric terms, okay? So let me go over that really quickly in this framework. The most basic RD design, I'm gonna use prices as an outcome because we've been doing so many hedonic regressions. I want to come back to your question about taxes in a minute too. You have a bunch of different points. They have a distance from the source, and they also have a house price, and they have a bunch of other x's. All you're doing is regressing your observed outcome, let's say prices, on a dummy variable equals to 1. Over here, and it is all matters, the specific framework or setting you're in of how you categorize which side is the high side. Here it's pretty straightforward because the data shows the prices are higher over here, the jump is higher. But you have the research part of it is you have to kind of determine which is going to be the high side before you can look at the data, right? I mean, all of the points have a positive distance from the source. Either whether they're going east or west, the distance is positive when you pull it out of the machine GIS. You say, okay, give me the distance from these points to the source. It's going to give you a positive distance, obviously. And then you say, well, all the ones on this side where house prices are higher, I'm going to make distance positive. And then all the ones on this side where they're lower, I'm going to make distance negative. And then you can set up the data so that it's just running across this distance axis, and you can visualize the fact that your outcome changes once you cross this threshold, which is the boundary. All this does is say, well, what is the jump in prices when you go from here to here? It's going to be this discontinuity. So this is just, the magnitude of this jump is just alpha 1 hat. Obviously, the distance to the boundary matters on both sides of the source. So you have a control for distance, and then you have a control for a distance on the high side, right? So you know that there's going to be omitted variables that could vary with distance and affect the price. And so you put a control for distance in the regression. And I mean, at the most basic, this is the most basic RD. You're just seeing what's the change in your outcome moving from one side to another. Okay? Any questions so far? Because we talk about the assumptions and then we'll be done. And then you'll get more of this on Tuesday. So the considerations, the functional form, so in terms of distance, the effect of distance on prices could be linear, it could be quadratic, it could be cubic, okay? If we were to look at these plots and say, well, what functional form should we have the relationship for distance and the outcome? Probably a square term, right? This looks like a parabola, so we'd say, well, distance is the omitted variable based on the raw data for prices. We just assume that it follows a quadratic relationship with prices. Okay, but you have the choice, and depending on the setting, if you're going to allow this functional form to be linear, quadratic, or cubic, trying to model the unobservables. The second one is the bandwidth selection. And this is all just a warm-up for your next class. Bandwidth selection says we have units of measure or observations along the distance line. How close should they be to the source for the treatment and control to be relatively similar? Okay, so there's plenty of different econometric tools to do this now. Maybe this is your bandwidth. And you say, well, look, we have a lot of data out here that we can't use because they're not comparable to each side of the boundary. But in principle, those that just are on this side of the boundary are very similar to those on this side of the boundary. You say that type of thing. It's an ad hoc choice you can make, or you could use the software. There are like certain bias minimizing bandwidth estimators that you could get. Well, you'll learn about that on Tuesday. And so this goes for the boundary discontinuity design and just your standard regression discontinuity designs. The choice of the bandwidth is super important because it determines who's being called a treated and controlled unit, right? And you want to make sure your results are not sensitive to your choice of bandwidth and your choice of functional form. Okay, so this can be written a number of different ways, and obviously it can get more and more complicated. This is the most basic way to think about it. Okay? All right, perfect. Interesting stuff. On Tuesday, you will get a lecture. I'll send you the notes in advance. I'll be attending. How should we do it? Do y'all want to meet here all together and have her pulled up on the screen for the virtual presentation? It seems like most of y'all are on campus on Tuesdays anyway. Is it? Yeah, I think that's probably the best way to do it for accountability.
Yeah.
I tell y'all to watch it at home, just